So far we have talked about velocity and acceleration in an absolute sense. Let us now discuss the relative motion of two particles using a translating axis. So when do we have relative motion? Well, relative motion occurs whenever you have two particles that are both moving, and we are interested in knowing the velocity of one particle with respect to the other that's also moving. And so this approach is useful when dealing with complicated problems in which the motion of the point of interest is the combination of multiple simple motions. So this combination can be a combination of rotation and translation. And one simple example could be a point of interest which is attached to the propeller of an airplane. So let us imagine an airplane that is translating at a certain speed, and we know that the propellers are also rotating at the same time, and we actually want to define the motion of the point of interest which is attached to the edge of the propeller. So obviously this point will undergo a rotation and the translation at the same time. So its motion would be a sort of spiral that moves. And so in order to analyze this motion in a simple way, one can make use of the relative motion analysis. And so the goal is to analyze the motion separately using two or more reference frames. So you can attach a reference frame onto the plane, you can attach a reference frame onto the propeller, and attach a reference frame onto the ground, and you can start to sort of relate the different motions in terms of one another. And so the final motion is obtained through the vectorial additions of the different components. So once you have the translating motion and the rotating motion, the final motion in absolute terms would be the sum of these two. But one should keep in mind that the superimposition requires the knowledge of the positional relationship between the different reference frames. So there's no way you're going to be able to sum the different velocity accurately unless you know how the position of one reference frame relates to the other. Let us now look at an example that would help clarify the previous discussion. Let us assume that we have three different individual O, which is fixed, individual A, which is moving, translating, and individual B, which is also translating. Now let us assume that O has no means to see B, so it cannot know where B is located, but can only see A and talk to individual A. Now if one needs to find the position of B relative to O, so O needs to try to estimate the position of B by simply talking to A. And so in simple terms, one can say that the position of B relative to O is equal to the position of B relative to A plus the position of A relative to O. So let's say that O knows that A is 1 meter away in that direction, and that A answers the question by telling O that B is 2 meters away from A in this direction. By simply summing these two values, the position of B relative to A, which is denoted RB relative to A, and the position of A relative to O, RA relative to O, one can know the position of B relative to O. And so mathematically, one can write that RB relative to O is equal to RA relative to O plus RB relative to A. And now if we assume O, given that it's fixed, to be the main reference frame or the absolute reference frame, one can write that RB, the position of B in absolute terms, is equal to the position of A in absolute terms plus the position of B relative to A. Now this is the main expression for relative motion analysis, and in order to sort of remember how the different terms come in the equation, one can look at the subscripts of the right hand side. So we have A and B over A, and by taking the multiplication of those subscripts, you should always end up with the subscript of the left hand side. So in this case, we have A times B over A, then A and A cancel out and you're left out with B, and so you know that the equation you've written here is actually the correct expression of relative motion.